that have to do with spin. Really, that's the subject of the end of chapter 4, but we are, essentially talking about finite dimensional vector spaces and operators on them now. I don't think Griffiths talks anything about spin, but we'll talk about spin because you know about from modern physics, and then we'll elaborate on it significantly at the end of chapter 4. But first, this question that I think I brought up at the end of last time. What do we need matrix elements for corresponding to these operators, position and momentum? We've got perfectly good expressions, x and minus I h bar d dx, that are ready to operate on some psi of x, maybe at time t equals 0, right? This is our position representation of the state of the system, and these are ready to operate on it. Why would we need the matrix elements? And the answer is, really, we don't need them in this particular case. For more general kinds of operators, you do need them. You can't always get sort of a shortcut method like we have for this, but somebody gives you a function of x, you know how to apply both of these operators. You don't need to think about matrix multiplication. But in general, the matrix elements tell us how to apply an operator in a particular representation. I should also say that Griffiths has some comments in there. Part of it, I think, is in a homework problem that I didn't assign, but you can show, and Griffiths leads you through it if you want to see the details, that there's a similar kind of representation of x and p operators in the momentum representation. In other words, if you know phi of p, the momentum space wave function, then the position operator is given by plus IH bar ddp. And the momentum operator is given by just the multiplication by p. So it looks like almost the same thing, except they kind of switch and all the x's go to p's over there. But it is kind of instructive to still think about what the matrix elements of x hat and p hat look like in the position representation. So let's just calculate them. And you can see that they're doing the same thing as taking a derivative or multiplying by x. Let's first just calculate what the position operator matrix elements are in the position representation. So that means I sandwich the operator between two states of definite position. Okay, and then I write that usually to calculate what the matrix elements are. In most cases, I have to go to the integral kind of representation. So I say, well, what are the states of definite position in the position representation? Well, they're Dirac delta functions. So I have a delta of x minus x2 is the state of definite x2. Delta of x minus x1 is the state of definite x1. And I sandwich the position representation of the momentum operator in between. And I've got to do that integral, which looks a little bit befuddling. And when Griffiths does these integrals, and I'm not going to say anything more about it, he still uses the good old property that if you got a delta function sitting next to some other function, let's just substitute the location where the spike is in for the other function. Now, our proof that that worked fails in this case because you have to assume the function is continuous, and the Dirac delta function is definitely not continuous. But nonetheless, you could make the argument rigorous by saying we have a very narrow but perfectly continuous function that represents the Dirac delta function, and you have to think carefully about what happens in that case. In any case, if I just use that property and say, well, I've got an x times delta of x minus x2 next to a delta of x minus x1, and that means I can just evaluate this function at x equals x1. X times delta of x minus x2, evaluate at x equals x1. And I get this. And then I've got to think about that. So these are the matrix elements. They should be a function of x1 and x2. Those are continuous variables. And what does that look like? You guys help me sketch this. So we just found out that the matrix elements of the position operator as a function of x1 and x2 have the form x1 delta of x1 minus x2, and I would like to now envision that as some sort of matrix. Okay, so what goes on this axis here, the x1 or the x2? x1 goes on there because this is always row and column. This is the row index. This is the direction that tells me which row I'm in. So that's the row index increasing along there. This is x1. This is x2. Maybe we'll just, to kind of orient ourselves, there's an origin somewhere. We have the complete x-axis. There's no upper left corner to this matrix, even though it kind of looks like it does. Where are there zeros in this matrix? Say that again. I still couldn't hear anything, but maybe it's my hearing. Yeah, everywhere except on the diagonal, right? So everywhere except on this line, it would have to go through 0, 0, I guess. So there's a line right there. That's the line x1 equals x2. That's the only place where this function is not 0. Everywhere else it's 0. So I've got a big 0 in this whole region up here, 0 down in that region. And then, you know, well, you can think about what happens as you go through there, right? If I vary x2 or something like that, right? If I vary x2 for a particular value of x1. So here's a particular value of x1, and I'm going across and varying x2. It's only when x2 equals x1, that's right on the diagonal, that I hit some Dirac delta function like that, right? There's another Dirac delta function here. Now, a normal Dirac delta function has area 1 under it, but this one's area, you know, when it gets multiplied by 3, it has an area 3 under it. So this one has an area that varies under the delta function as you go along. It would have area 0 under it at the origin, getting bigger and bigger area under it. I'll leave it to you to think about why that is the same as just simply multiplying by x. Clearly, it doesn't look as easy as multiplying by x, right? I don't want to take this matrix and have to do an integral that represents matrix multiplication when I could simply just multiply by x. So we always want to use that shortcut. What about the momentum operator in the position representation? Let's try doing the same thing. So here I've just sandwiched, same kind of thing. I'm just sandwiching the momentum operator between these two states of definite position and trying to do the integral. And let's think about how to do the integral. Here I've got something over here, and it's next to a delta function. And without worrying too much about the stipulation that that function should be continuous, let's just evaluate this function at the value where this blows up, and that's at x equals x1. So evaluate this at x equals x1. Well, I've got a derivative of a Dirac delta function, and then I'm going to evaluate that at x equals x1. So that's going to give me the derivative of the Dirac delta function with argument x1 minus x2. And then there's a minus IH bar that, of course, comes outside the integral, so it comes along for the ride. What does that look like as a function of x1 and x2? Let me just erase. Where is my eraser? Did I steal it somewhere? I don't think I've used it yet. There's got to be an eraser in here somewhere. But this is the only chalkboard. I know Dr. Neiser was in here yesterday, but I don't know why he would have carried away the eraser. Hold on for a second. Let me grab one from the Physics 110 lab. So again, well, I guess we need to figure out what a derivative of a Dirac delta function looks like. So we just found out this. The momentum operator matrix elements in the position representation look like a constant. I'm not going to worry too much about the constant, but times the derivative of the Dirac delta function evaluated at x1 minus x2. So I guess first of all, if I know a Dirac delta function looks like this, as a function of x, delta of x minus x1 as a function of x, here at x1, our kind of model is a very narrow Gaussian or something like that, right? Sharply peaked Gaussian. What would the derivative of that function look like? Well, it's 0 over here, right? The derivative is 0. And then all of a sudden it gets extremely positive. And then suddenly it becomes extremely negative. And then it goes back to 0. So it kind of, here again is x1. It goes very rapidly positive and then very rapidly negative and then back to 0. So a derivative of a Dirac delta function kind of looks like that. So again, similar kind of structure, except as you go across the diagonal, that's the only, so this function, just like this function, is only non-zero when the argument is 0. And so that means this is only non-zero when x1 equals x2, which means we just have the diagonal elements, but as I go across there, I go up and then down and then back to 0. And it's not so surprising that the effect of this matrix multiplication is taking a derivative of a function, right? Because what I want to do when I take a derivative of a function, if I put this next to some continuous function over here, right, that's doing whatever it's doing, and I want to take the derivative at a particular value of x, I should be evaluating f at x plus delta x minus f at x. Now this one seems to have the minus sign in the wrong place, but we also have a minus sign out in front, so it's not, we could think about the details there, but it's sort of subtracting off the values of the function at very close locations, right? The location here minus the location there. So it seems like it would affect something like a derivative. Well, maybe we need to think more carefully here, right? Let's suppose here is, if this is 0, maybe this is x1 equals minus 3, right? So if I want to find, and let's forget about this constant because it's sort of a little bit confusing. We'll just consider delta prime of x1 minus x2. If I want to find it at minus 3, what I've got to do is take this entire row and multiply by this entire column. In other words, multiply those little by little. And what that means is when I multiply it, I'm going to multiply all this stuff times 0 until I get to the point on the function which is at minus 3 here, right? And then it's going to take the difference between adjacent points on there. And at that particular location. And what that means is the result, when I do this matrix multiplication and I get a result over here, what we're finding out is what goes in the minus 3 position. And we're saying it corresponds to a difference between very close locations of this function centered around x equals minus 3, and that's what goes there. And of course, when you take the derivative, you do f of x plus delta x minus f of x. divided by delta x. And so you take that difference between close by points, but then you divide them by an extremely small number, which makes them very big. That's why we've got a huge number multiplying these adjacent, difference between the values of the function. In any case, we can talk more about it offline if you want to think more about that. But the upshot is, don't do this. We already know how to let it operate on there, but it's sort of interesting because, a lot of these matrix elements of operators that we use a lot do end up having these delta functions, derivatives of delta functions, second derivatives of delta functions, if you thought about the kinetic energy operator or something like that. But we're not going to have much of an occasion to use them. All right. Now, on to the next section where, there's a lot of little sections in here, and each one is almost like a bigger section in this chapter. We're now going to talk about, in great detail, finite dimensional Hilbert spaces. We've been talking about continuous, infinite dimensional vector spaces with discrete sets of basis vectors and continuous basis vectors. What about good old finite dimensional vector spaces? What about, our vector we're talking about could be a vector in 5 dimensions. Its components would be written as a column vector with 5 elements, for example. That's the kind of thing we're talking about. Your good old friend, right? We're used to this, especially if you've taken linear algebra. You do a lot of stuff in finite dimensions. So the matrix elements on this are good old 5 by 5 matrices if we're talking about a 5-dimensional vector space. Okay. And the major application in quantum mechanics, the reason it's so important is because of spin, to describe spin and how, well, we'll talk about how to think about them, how a spin state, say, of an electron changes as time goes on. So here's some facts from modern physics. If you choose some plus z direction in space, and it doesn't really matter, but you have to be definite and say, this is going to be my plus z direction. And we're talking about an electron, which is called a spin 1/2 particle. Then if we measure its spin angular momentum z component, and we call that sz, we can only get one of 2 values, plus h bar over 2 and minus h bar over 2. The plus h bar over 2 state we call the spin up state of the electron, and the minus h bar over 2 state we call the spin down. So this sounds like a 2-dimensional vector space, right? We've got 2 different states, and quantum mechanically, of course, this the electron could be in a linear combination of those, right? It can't just be in one or the other. Maybe it could be in 1/√2 times spin up plus 1/√2 times spin down. So weird stuff happens in quantum mechanics. Now, we already know, and we'll talk about this more in just a second, that the real state of the electron not only has a spin state, but it's doing something spatially too, right? So if we want to describe the whole electron, we need to say what's happening to its spatial wave function as a function of time, and also what's happening to this 2-element spin description as a function of time. We are just going to ignore the spatial stuff for now. That doesn't mean it's not important, but maybe we're just focused on spin for something. So we're going to just specialize to the spin aspect of the electron. And there are only 2 linearly independent states, and we're going to describe them as column vectors with 2 elements. We'll describe, by definition, the spin up state we're going to say is 1, 0. Griffiths denotes that as an abstract vector with a plus in it, spin up. And 0, 1 is the spin down state, and that's minus. So that's a particular basis for this vector space. And in general, an electron doesn't have to be in a spin up or spin down state. It could be in a linear combination of them. So the most general state of an electron is 2 numbers put there. Generally, we like to normalize the spin state, just like we like to normalize every other state. So we're going to always make the magnitude of a squared plus the magnitude of b squared equal 1. But you have a lot of freedom in choosing that. And the question we want to address here is, if we know what the spin state is at time equals 0, suppose it's in the state AB at time equals 0, right? Maybe it's 1 over root 2 and 1 over root 2. That would be a normalized state. Then how does that spin state change with time? In other words, if it starts out in that state, it might not stay in that state. It might change with time. We've got to figure out what happens. Okay, and so I want to go back and make a little discussion now about how do we figure out how things change with time? Well, we know how to do that in the case of the spatial wave function, and we're now generalizing to a case where we're not just keeping track of the spatial wave function, but also the spin state. And so we're going to describe that as a product state where we describe, instead of just writing a spatial wave function, we'll also have a 2-element column vector there. And both of those presumably are going to change with time. What determines how things change with time is the Hamiltonian, right? Because we're used to putting in that factor e to the minus I ENT over h bar, and we need to figure out what those ENs are. Those are eigenvalues of the Hamiltonian operator. Now, in the vast majority of simple situations, the Hamiltonian has to tell us something about the spatial part, and we're familiar with this old part, right? This is usually what we call our Hamiltonian. I'm now going to call this, just for the sake of keeping things straight, the spatial part of the Hamiltonian. And the idea is it only acts on this function of x over here. In other words, if this is sitting in front of it, that stuff would just pass right through it. It doesn't even care about this. This stuff just comes along for the ride as the spatial part of the Hamiltonian is concerned. Similarly, if this is what about, the energy of the spin state might depend on the spin state. There might be some potential energy. And you talked about this in modern physics, right? Where if you take a spinning object, right? And that's spinning, let's imagine a sphere of charge, right? And it's spinning. This isn't the quantum mechanical picture, but the classical picture. I got a spinning sphere of charge. We're going to imagine electrons like that, right? I've got some currents, right? And those currents create a magnetic field. And that gives this thing what's called a magnetic moment. And hopefully you remember something about it. If you put something with a magnetic moment in a magnetic field, there's a torque that tries to align the magnetic moment with the magnetic field. So this is a state of higher energy when it's pointed against the magnetic field, and there's a state of lower energy. Now that's for the magnetic moment. That's not the spin. If you're talking about an electron, and generally negative charge particles have this, you have negative charge spinning in this direction. That corresponds to a magnetic moment in the opposite direction from the angular momentum. But in any case, the energy might depend on the state, the spin state that you're in. And we're going to describe that potential energy that might be generated between there by a 4-element matrix, 2x2 matrix. It might not be diagonal because, I might have chosen plus z to be this way, and then I might apply a magnetic field at a weird angle off to the side. And so it's, a spin up state and a spin down state aren't necessarily either one aligned with the magnetic field. But we're describing it as a 2-element vector, so this seems like the most general linear operator that we could think about, right? And when this acts on this state, it just ignores the spatial part and only acts on the column vector, not surprisingly. All right, how do we get the time dependence in there? Well, here's what you know, right? This is a review of chapter 2. When we did separation of variables, we said, if we can write psi of x0 as a linear combination of states of definite energy, in other words, eigenfunctions of the Hamiltonian, then to get the time dependence in there, we just put the corresponding exponential thing in each term with the correct energy eigenvalue in there that corresponds to this energy eigenfunction that's sitting there, right? That's what we used to do. Now we've got this more complicated state that also has a spin description, right? And the idea is at time t equals 0, so this is what it's in at time t equals 0, we want to write it as a linear combination of all of the eigenvectors of the Hamiltonian. Now we're going to call the eigenvectors of just the spatial part of the Hamiltonian, the good old psi-n's that we're already used to, right? So if you just look at the spatial part and find its eigenfunctions, we'll call those psi-n's. But we're also going to need to find the eigenvectors of that 2 by 2 matrix. And so those eigenvectors will correspond to eigenvalues, and we're going to do that in just a second. If you haven't taken linear algebra, maybe you've never done that before, but we're going to say, given that Hamiltonian, if we know those 4 numbers that are in that 2 by 2 matrix, how do we find its eigenvalues? Well, it will turn out that in general, there are 2 different values, and I'm going to call those the spin part of the Hamiltonian, energy 1 and energy 2, 2 spin energies that are allowed. And there are some corresponding eigenvectors. So this alpha 1, beta 1 is supposed to be the eigenvector of that ABCD matrix that corresponds to a particular eigenvalue. And here's the other eigenvector that corresponds to that value. And we have to allow, so, the most general state would be psi n times the first one of this would be one state, and then psi n times the second one of these would be another state with a different energy, right? Because the total energy is the energy En plus the energy of this state that you've put there. Okay, so all I'm saying here is at time t equals 0, I've got to write this as a linear combination of the product of psi n times these definite energy states that are eigenvectors of that ABCD 2 by 2 matrix. Similarly, these CNs up here, just to remind you, right? We said if we normalize this spatial part of the state, we'll find out that the CNs are normalized as, sets of numbers in little L2, space of square summable sequences. They'll be normalized in that if you sum up all their squares, they add to 1. And that means that each one of those has an interpretation as a probability. So the magnitude of Cn squared is the probability that a spatial energy measurement yields spatial energy eigenvalue En at time t equals 0. The interpretation of these C1s and C2s is going to be the same thing. If we start out with a normalized 2-element vector, then the sum of the squares of these 2 coefficients out here are going to equal 1. And they each have the magnitude squared of C1 has a probability interpretation. Same thing with C2, but I didn't want to write it twice. If you measure just the spin part of the energy and it yields the first of the 2 eigenvalues at time t equals 0, it will do that with this probability. So the magnitude of these numbers squared has a probability interpretation too. Now, this all seems very complicated, but I'm going to try to pull it together so that we can just specialize to just the spin stuff, and we won't have to worry about the spatial stuff. Okay. Now, how do I put in the time dependence of a state like this? Well, the same way we did before. We say, take each term in the series. So one term in the series might be this one for index n here multiplied by this one. This spatial wave function multiplied by this second one is another term in the series. We take each term in the series at time t equals 0, and to put it in the time dependence, what we do is multiply by e to the minus I e t over h bar, where e is the energy of, for example, the psi n multiplying this first 2-column vector. Well, that one corresponded to energy e spin 1. So the total energy is just going to be the sum of the spatial energy plus the spin energy. And the same thing for the second one. Spin energy presumably is different for the second one. All right. And to make our life a little bit more simple, we can see we have a common factor of e to the minus I e n t over h bar in both of these two. And so I could factor that part of it out in front and just leave the part with the e spin 1 and the e spin 2 in with these 2 individual vectors there. Okay, let me color code things and then we're going to forget about most of this mess, but it's a justification for it. Notice I've put the spatial stuff here in blue, and I've put the kind of spin descriptions in red here, right? So here's what it is at time t equals 0. The red stuff is the spin state at time t equals 0. How do I get the spin state at time t? Well, what I do is just take the spin state at time t equals 0 and multiply by just e to the minus I e t over h bar, where e is the corresponding spin eigenvalue to that eigenvector that we found up there. And same thing for the second term. So when we're specializing to just spin and we're going to ignore the spatial part, the idea is I put in the time dependence the same way, and I just forget about the fact that there's a spatial part. I don't worry about these other energies that are associated with the spatial part. I just need to find the eigenvalues of that 2 by 2 matrix. And then to put in the time dependence, this tells me how to do it. Okay, so back to our problem here. Let's do an example. Let's suppose the spin Hamiltonian is 1, 2, 2, 1, just to make a nice simple matrix. You could put in energy units if you wanted to feel better about it being dimensionally correct. That's just the spin part. I'm not going to tell you anything about the spatial part because we're going to ignore it. We just justify the fact that we can ignore it. And maybe that's due to some applied B field, right? You've decided on your Z direction, but then you applied it. If you put your B field along the Z direction, you would get a diagonal 2 by 2 matrix. But if you put it at some weird angle, then you're going to get off diagonal elements in that Hamiltonian as well. Okay, and the question is, if the electron starts out in a particular initial state, so I'm going to say, suppose it starts out in the what we're going to call the spin up state. Its spin angular Z angular momentum is plus h bar over 2. So it starts out in this state. How do I find out how this evolves with time? Does it just stay at 1, 0? Okay, if it starts out in this state, won't it stay that way forever? The answer is, in this case, it won't. Why not? How would you put that into words? Or how would we test whether it would stay that way forever? Under what conditions of me choosing a vector here for the initial state would the probabilities not change with time? Think of the spatial case, right? Suppose we have the infinite square well, and I say, give me an initial state where the probabilities are just going to stay the same forevermore. You could choose anything, right? You could choose some box-shaped function like that. That one's not going to work. What ones would work that would keep the same probability distributions as a function of x? As what's that? Stationary states, right? States of definite energy, or more to the point, the energy eigenvectors of the Hamiltonian. So the question is this an energy eigenvector of the Hamiltonian? I mean, it's a question. We have to, write down the eigenvector equation, eigenvector eigenvalue equation, but we can test it, and we're going to find out it's not. And that means at a later time, maybe the second element isn't 0 anymore, and the first element's a little bit smaller, right? The sum of their squares is always going to add up to 1 if I start with a normalized state, but they're going to change as time goes on. Okay, so are those two states eigenvectors of the Hamiltonian, the 1, 0 and the 0, 1? No, they're not. We'll find out in just a second. And so the idea is, if we knew the eigenvectors, we're going to use that process that we did before. Write this state as a linear combination of the energy eigenvectors of that 2 by 2 matrix, and then put in the corresponding e to the minus I e t over h bar factor in each one of the terms. Okay, so let's do that. I'm going to do it once on the board, and then you guys are going to do a worksheet if we have time. So let me find the right page here in my notes. I'm following along an example, but I just want to be able to write it sort of more slowly. So again, our Hamiltonian is 1, 2, 2, 1, and our initial goal is to find the eigenvalues and eigenvectors of the Hamiltonian. That means I got to write down the eigenvalue equation, right? The eigenvalue equation is H, sort of generically, H psi equals E psi. Let's write that in terms of our given Hamiltonian and the 2 element vectors, right? So I have 1, 2, 2, 1 times some unknown alpha beta that I want to find. And that has to be E times alpha beta, right? I'm just going to write that as E times alpha, E times beta. Okay. And well, some of you may have taken linear algebra, some not, but the idea is if you want to solve an eigenvalue equation in finite number of dimensions, what you do is subtract everything off so it's all on one side and you set it equal to 0 over here. So I'm going to subtract this vector off of both sides, and that gives me 1 minus e 2 to 1 alpha beta equals 0, 0. Sorry, this should be a 1 minus e also. And again, if you've taken linear algebra, we don't have time to explain it now, but there's a sort of a geometric way to think about this. If a linear transformation on your vector gives the 0 vector, unless one of two things has to be true. Either this is the 0 vector, and we're not interested in the case where this is the 0 vector, because then it wouldn't be considered an eigenvector, right? The 0 vector is never an eigenvector. Either this is the 0 vector, or the determinant of this matrix has to be 0. Okay, and so we're just interested in that second case. So if you've taken linear algebra before, you may have memorized something that says, oh, if you want to find the eigenvectors and the eigenvalues of this equation, the first thing you do is write down the determinant of this matrix with the eigenvalues subtracted off along the diagonal is equal to 0. The determinant of 1 minus e 2 to 1 minus e has to be equal to 0. And that, when I expand it out, is usually called the characteristic equation corresponding to this eigenvalue problem. So let's do that. You got to remember how to do determinants. 2 by 2 is pretty easy, right? I do 1 minus e times 1 minus e. So I get a 1 minus e squared minus 2 times 2, which is 4, and that equals 0. So that means 1 minus e squared is equal to 4. How would I solve this equation? This is the kind of thing I asked Physics 110. How would I solve this equation? Should I square it out and then use the quadratic formula? No, right? I mean, this is what we've already done, what's called completing the square here. So we just want to take plus or minus the square root of both sides, right? So that means that 1 minus e is equal to plus 2, or 1 minus e equals minus 2. 1 minus e equals plus or minus the square root of 4. That's all I did there, right? And that gives me 2 values of e. Those are my energy eigenvalues. Okay, so that means e is equal to minus 1. E is equal to minus 1. Or in this case, e is equal to 3. Those are our energy eigenvalues. So that's the first step. Solve what's called the characteristic equation for the eigenvalues. And then those of you who are linear algebra people, how do I then find the corresponding eigenvectors? Substitute them back in, right, into something like this. I could use this equation if I like, right? So let's take those two values one at a time. So let's take e equals minus 1. I just should make sure, yeah, I agree with my eigenvalues in my notes. So let's specialize to the case e equals minus 1. And I'm going to substitute them into this equation right here. If e is minus 1, then this looks like a 2 up there, right? Yes. So this equation becomes 2, 2, 2, 2. We're subtracting off minus 1, which is the same thing as adding 1, times alpha beta equals 0, 0. And that gives me two equations. You can see they're exactly the same equation, right? I'm going to get 2 alpha plus 2 beta equals 0, or 2 alpha and 2 alpha plus 2 beta equals 0. And if you've done this before, you know the two of these are always linearly dependent, right? For the 2 by 2 case, the last one is always dependent on the one before. So you don't get anything from the last equation in doing this. So the only relation I can get from this is that 2 alpha plus 2 beta equals 0. And one way to, I could divide by 2 right away and then find out that beta has to be the negative of alpha. Okay. So that means that, I might I'm not sure why I'm calling these states psi minus. But I would probably, if I were to use Dirac notation for the eigenvectors, I might, say we're finding now the eigenvector corresponding to E equals -1. So maybe just to remind myself what that means. And what did we find out about these two numbers? Well, I could put in something like this, right? Beta is minus alpha. That's not normalized though, right? How do I normalize it? What factor do I need out in front? 1 over root 2, right? So I can put the 1 over root 2 in there, but people conventionally just put it out in front. You can multiply it through and then square them, and you're going to get 1/2 plus 1/2 is 1. So then it would be normalized. So that's my normalized E equals -1 energy eigenvector. Then I do it for the second one. So let's just run it through. E equals 3. Okay. Taking this equation, when E equals 3, I get a -2 there and a -2 there. So that looks like this: -2, 2, 2, -2, alpha, beta equals 0, 0. And again, the two equations are the same. If I just write down this one times this one gives 0, that gives me 2 alpha, -2 alpha plus 2 beta equals 0. And that's telling me that alpha equals beta. Okay, and that means the corresponding eigenvector is corresponding to E equals 3, can be represented by this 2-element column vector, which is 1, 1, and then I'm going to normalize by put a 1 over root 2 out in front. So that's a normalized eigenvector. So these two eigenvectors are normalized, and they're a basis for our two-dimensional vector space. Of course, 1, 0 and 0, 1 were also a basis, but we're not interested in that basis. We're getting a new basis that actually corresponds to stationary states. All right, so now how do I finish up and figure out if I'm in the state 1, 0, how do I make that time dependent? What's the next step? That's my initial state. We said initially it's in the spin up state. We found out it's definitely, the state it's in at time t equals 0 is definitely not a stationary state. So it's going to change in a profound way with time. How do I figure out how it changes with time? What did we say? Okay, so what do I do over here? Do I just put an e to the minus I? E, well, what e should I use? T over h bar. There's a step I have to do before that, right? It's sort of like we know psi at time t equals 0. I can't just put the e to the minus I et over h bar in front of that. I first have to expand that as a linear combination of definite energy states, right? And then in each one of those terms, I know which e to put in it because there's a certain n for each one of these, right? A corresponding en. So my first step is to write 1, 0 as a linear combination of these two energy eigenvectors. Those are our stationary states, right? How did I write it in the notes? That must be on the next page. I wrote the constants as a and b. So I want to write this as some constant times 1 over root 2, 1, 1. plus some other constant times 1 over root 2, 1 minus 1. And that's a system of two equations, and I've got two unknowns, A and B. I want to figure out what those A's and B's are, right? So that's telling me that 1 equals A over root 2 plus B over root 2. That's the upper row. And then the lower row is telling me that 0 has to be equal to A over root 2 minus B over root 2. And at this point, it'd probably make my life easier just to multiply both of those equations by root 2 to get all those root 2's out of the denominator, right? If I multiply by root 2, this would go away, this would go away, and this would turn into a root 2. And if I multiply this equation by root 2, 0 doesn't care, it's just still 0. Okay, so that's equivalent to those two equations. And now what's the easiest way to solve for A and B when you have a system like this? You could, if you're in physics 110, everyone would say you do substitution, but there's an easier way here. What do we do? Yeah, I add them and then I subtract them because, I can see when I add them, the B's are going to go away. When I subtract them, the A's are going to go away, and that immediately gives me the two solutions. So when I add them, I get root 2 equals 2A, and that means that A is equal to 1 over root 2. And when I subtract them, these go away. Root 2 minus 0 is still root 2, right? The A's go away, and I get B minus B, that's 2B. And that means B is also equal to 1 over root 2. Okay? So that means my expansion here, I'm just going to substitute those in. I've written 1, 0 as a linear combination of this state and this state. And these are the coefficients that we need, those C's. And now I can put in the time-dependent state, right? If I wanted to say, what is, the upper one as a function of time and the lower one as a function of time, it should reduce to 1, 0 if I plug in t equals 0. I need to multiply this one here times, I didn't leave myself enough room, e to the minus I. What's the e that I'm going to put in there that corresponds to the 1, 1 eigenvector? 3, right? This 1, 1 eigenvector corresponded to e equals 3. I left out the units of everything here. So I put a 3, there might be some units with it or something like that. T over h bar. And this one gets multiplied by e to the minus I and minus 1. So that would be plus I t over h bar. And now I could put those together all into one glorious two-row column vector. Let me erase this stuff down here and let's combine it all together. Of course, this is just 1/2. This is also a 1/2. So this looks like, I'm just going to write it as one big column vector. 1/2 e to the minus I 3t over h bar plus 1/2 e to the I t over h bar. And down here, I have 1/2 e to the minus I 3t over h bar minus 1/2 e to the I t over h bar. So that's telling me explicitly what A of t is and what B of t is. That's how those are going to change with time. And so you might be able to find times. Let's see, when I plug in t equals 0, this is 1/2 plus 1/2 is 1. When I plug in t equals 0, this is 1/2 minus 1/2 is 0. So it gives me the correct t equals 0 state. But then those numbers up and below are going to change as time goes on, as those complex exponential functions sort of beat against each other. All right. What time is it? 1:31. We can get started on this worksheet. Any questions on that while I'm passing this out?
Dr.
Oh, don't
Philly,
tell me. I've forgotten my worksheet. Did I? That's unfortunate. Well, give me 30 seconds and I'll go get it from my office. Well, of course, when I'm looking for something in a rush, I can't find it, but I think I know what the problem is, and you'll see it here. Here's the worksheet. It's the same as what we're doing, but the Hamiltonian is different. Here it's 1, 2, 2, 4. And what you can't see there is, I think the initial state is 0, 1 rather than 1, 0. So take the initial state to be a spin down state. Take the Hamiltonian to be 1, 2, 2, 4, that 2 by 2 array that's shown up there, and then find how the linear combination of spin up and spin down changes with time. And it's really a matter of just trying to do this stuff yourself, which you should be able to do, and you'll get some practice for it. If you're on Zoom, this was posted, I think, for Monday's class. It was probably worksheet 2 for Monday. We just didn't get there. The initial state is 0, 1, spin down state. The exact opposite of the one we used here. Here we used 1, 0. The initial state is 0, 1. That's what it's saying up here in the text. At time t equals 0, the electron's in a spin down state. We're ignoring the spatial part of the wave function and just focusing on the spin part. And I've given you the spin part of the Hamiltonian. And we want to find the time dependence of that. So see, I mean, I guess the challenge in the last 5 minutes is to see if you can find the eigenvectors and eigenvalues of the Hamiltonian. So see if you can quickly bust those out. So the shortcut always is, if you want to find the you're trying to solve this equation, subtract off E along the diagonal of the Hamiltonian and multiply that matrix times some alpha beta that you want to find, and it should set it equal to 0, 0. That's sort of always the way we're going to start. And the next step is, that means the determinant of this array has to be 0. And solve the resulting equation. I think I chose, just like in this case, you won't have to use the quadratic formula. In general, you are going to have to use the quadratic formula for a 2 by 2, but I've chosen numbers where it works out nicely, if I remember correctly. I'm going to show the board for the benefit of Alvis and Gracie. So it looks like the eigenvalues are 0 or 5. Some of you are nodding your heads and some are saying maybe not. I just wrote it on the board, but when I take that determinant, you get characteristic equation e squared minus 5e equals 0. I can factor out an e and then say either one factor has to be 0 or the other. So either e equals 0 or e equals 5. Those are the two eigenvalues. And now I've got to do the work to find the eigenvector corresponding to e equals 0. And remember, you can't have a 0 eigenvector, but a 0 eigenvalue is no problem whatsoever, as long as it corresponds to a non-zero eigenvector. So I plug those back into this equation up here. And when I plug in e equals 0 and work out what it says, it gives me that alpha is minus 2 beta. So I could put a minus 2 up, make beta equals 1, put a minus 2 upstairs, and then I've got to normalize it, take the sum of the squares of these things, and then take 1 over the square root of that. That will normalize it. So I get 1 over root 5 times minus 2, 1. There are different ways to express exactly the same vector that look a little bit different with just different numbers out in front. Second eigenvalue is e equals 5. And in that case, the characteristic equation gives beta, I'm sorry, the eigenvector equation gives beta equals 2 alpha. So the second element is twice as big as the first one. So my first guess is 1, 2. There's a beta that's twice as big as alpha. And then I normalize, which again gives me 1 over root 5 times that. There are different ways to write it that actually simplify to the same thing. And then the last step to get the time dependence in there is I've got to write our initial spin down state as a linear combination of those two we just found. Okay, so I just put constants a and b out in front. When you write down that system of equations, not too exciting, but you solve for what a and b are. A is 1 over root 5, 1 over root 5, b is 2 over root 5. And therefore, the spin state looks like this at time t equals 0. And therefore, at time t, I put in the corresponding e to the minus I et over h bar factors in there. And generally, it's a good idea then to write it just as one big 2-element column vector. And you can kind of see now, at least for this case, as time goes on, right, this complex exponential function is spinning around. When the argument 5t over h bar is pi plus a multiple of 2 pi, then this will be maximal and this will be minimal in that case. So every once in a while, the first element's going to be maximal, and that means you're most likely, if you measure the spin then, to get a spin up, right? When the z spin angular momentum, you're most likely to find plus h bar over 2. But as time goes on, this number is getting bigger and smaller in magnitude, and so is this one, and there's some of the squares always add to 1. Okay, and I'm sure, I hope that there's something in the homework that forces you to practice this one more time. And if there's not, it should probably be on the next exam practice material or something like that. All right, time's up. Have a good weekend.